So tonight's topic, I wanted to share attribute acceptance sampling plans. These are, when it comes to statistical methods, I very often get asked about attribute acceptance sampling plans, and we'll talk about where they could be used and why understanding the nuances and the ins and outs of attribute sampling plans is going to be important, both from the acceptable and rejectable quality level limits. And then finally, we'll show for those that use Minitab, we'll show how you can create and select your own statistical sampling plan if your procedures either don't have those sampling plans available to you, or if you need something a little bit more than what's already in your SOPs and work instructions. All right, so what we're going to go over tonight is what is attribute acceptance. We're going to talk about the ideal acceptance curve and how that can change when we go from, say, 100% inspection and testing to a sampling. What the impact is, the probability of acceptance, things of that nature. We're going to talk about the sampling errors that will be inherent in our sampling approach. And then we're going to walk through how to select and create a sampling plan, the appropriate sampling plan, and we'll walk through a Minitab example as well. So what is attribute acceptance? So let's start with that. First and foremost, we're talking about making an accept or reject decision of a population based on a percent effective. So we're looking at a particular attribute or characteristic of a part or a process, and we're going to calculate a percent effective, and we're going to make an accept or reject decision on that. And that could be through inspection, testing, or any other method of assessment where you're making a pass-fail decision. Common applications are going to be incoming material inspections, final lot release, process validation, and verification of CAPA effectiveness. This is one that I very often get involved in, just given the amount of CAPA work that I do. Now, let me just pause for a moment here. The reason why I wanted to emphasize and share this, because I do get a lot of questions on how to create these sampling plans. And for those that are in industry actively working in quality and using these plans, very often you'll have SOPs and work instructions. And somewhere along the way, somebody made it easy and created sampling plan tables so that you can look one up. The good news is it makes it easier to find sampling plans. The bad news is what we find is, when people are asking me questions, they don't have quite the understanding of what goes into an attribute sampling plan other than just looking it up on the table. And so some of that information is lost. That's what I want to share with you. I want to share how those tables were created in the first place so that if you do have tables you're looking up, you can then select from the different options with a little bit more insight. And if you don't have those tables available to you, we're going to show you how you can create some of those as well. I have seen some organizations where they only have A=0 sampling plans where you could only accept on 0 nonconformities of your sample, and we're going to show you tonight how you can create some of those others where it's A other than 0 and why you might want to do that. All right, so we need to start off first and foremost, take a step back on the ideal acceptance curve. What does this mean, the ideal acceptability? And what we're going to do is we're going to visualize our AQL, which is our acceptable quality level, my RQL, which is my rejectable quality level, and we're going to introduce this term LPD, the lot percent effective of the ideal acceptance. This is a curve, not the actual what's it called, the ideal step curve that I have here. You kind of have to do that manually, but these charts that we're going to see are ones that we can generate in statistical software such as Minitab. And I want to start with the ideal case. Okay? The ideal case, if we do 100% inspection or testing, and granted that we trust that inspection and testing, right? That it's good, that every time I'm inspecting or testing a unit, I am making the correct decision of accept or pass, right? So assuming that, we're going to go on that assumption. When I do 100% inspection or testing, this is what the ideal curve would look like. And in this example, just to kind of have an example to talk around, let's say that we're willing to accept a lot or a process that has a 5% or better nonconformance rate, or less than 5% or less nonconformance rate. Anything greater than 5% we want to reject. So that if I do 100% inspection of a lot and the percent defective is 5% or less, I have 100% probability of accepting it. I have all the information available. And again, I'm going on the assumption that I trust my measurement, I trust my assessment method. And if through 100% inspection, I've made an assessment, and that assessment is that the population is 5% defective or 5% defective or less, I will accept that 100% of the time. I will make that right decision. Similarly, if after doing that 100% inspection, I determine that that population is greater than 5% defective, I have 100% probability of rejecting that lot. Once again, I have all of the information that I need, trusting the measurement method. I have 100% of the information I need, so my certainty is 100%. So this ideal curve represents the 100%. We often don't look at this, but I want to start off with this visualization. This is what it looks like. And I'll even go as far as saying that, and again, this isn't something that we normally discuss, but if you can imagine the AQL and the RQL, the acceptable quality level and the rejectable quality level are actually equal in this case, right? Basically what we're saying is the AQL equals the RQL equals 5%, meaning that 5% or greater, I will accept, that's acceptable quality for me. Greater than 5% defect is rejectable for me. Now, keeping that in mind, I'm going to introduce the effects of sampling. Now, once I take a sample, I lose some of that information, right? We're basically taking a sample to make a statement about a population, but I'm losing some of that information. And that information can vary based on which samples I draw from the population, random sampling. And what we see instead, and I still have the ideal curve on here just to overlay it, but if I were to take a random sample, and in this case it's arbitrary, we're showing a sampling of n equals 29. I'm going to take 29 samples from the population, and I'm going to accept on 0. What we see now is instead of that perfect ideal curve of one side of the line, I have 100% acceptance. On the other side of the line, I have 100% rejected, probability of rejecting. What I have instead is this red curve. It's almost an exponential decay. It's not quite, but it looks like an exponential type of decay relationship. And what we're seeing is that the probability of accepting a lot is going to be a function of the LPD, the lot percent defective, the actual lot percent defective of the population, of which we don't know for certain, but we are going to take a sample. We're going to make a judgment call based on our sample. And what we could see here is that if we're running with that same example, if I have a lot that's exactly 5% defective, if it's exactly 5% defective, what I do is I go along the bottom line there where my lot percent defective on the x-axis, I hit the 5% and I go straight up. And I see that I hit that red curve around 20%, right? Meaning if I had a population that was exactly 5% defective, on this basic sampling, if I took 29 samples and I said that I will accept if none of them are defective in my sample, I will pass that sampling 20% of the time. Similarly, I will reject it 80% of the time. So you have that relationship between accept and reject. And I can see that, I can visualize that probability of passing my sampling, accepting, right, or passing that sampling plan will vary. So the better the quality, the better the actual quality, the better my probability of passing that sampling. the worse the quality, the greater the probability of me rejecting or failing that sample. That's going to be the premise. That's going to be the premise of what we're going to want to think about when we are selecting our sampling. So just taking a step back, why am I sampling in the first place, right? I alluded before, I want to make an estimate about a population. And sampling theory tells us that we can use a minimum sample to make a statement about a population. We could draw an inference about a population. And the question is always, how much is enough? And that's what we're going to explore. We're going to explore how much you need to make a particular statement. Every time somebody comes to me and asks me, right, how many samples do I need? I will immediately ask them, what level of quality do you want to demonstrate? Because it's the level of quality that you want to demonstrate that will tell me how many samples. From there, it's just math. But what we'll see is there are different sampling plans that we can put together based on that same level of quality that you need to make. And very often, that quality statement will be linked to the risk of the process or product failure. And what we'll want to do is create a level of confidence, a level of reliability or predictability that would be commensurate with that risk. So we talked about the effects of sampling and how that could impact my probability of passing. What that comes back to, those of us in the quality field, right, will recognize this table. This is, quality 101. You'll see this in your CQE or your CQM or whatever body of knowledge you're studying, right? It'll come down to this table, and it talks about the errors that we can make in sampling. Again, we're not talking about the error of misclassification of making a mistake. We're going to trust that the assessment method is quote unquote good and that we're making the right decision. But it's the error in the decision we could make based on the sample that I draw. Because if you can imagine, I have a population. When I take a sample from that population, I can get one estimate. And then if I resample, take a completely different sample, I can get another estimate. So I can get variation from time to time. And what we'll find is the decision that I make is highly dependent upon which specific samples I take. And these are the decisions we could make. One, first and foremost, I could make the actual decision. If we look on the left-hand side, my actual decision, I can either make an acceptance or a rejection decision. Along the top is, what should have I said based on the actual quality of the lot or the process that I'm sampling from, that I'm monitoring, or that I want to make an inference of. And we're going to go with the easy ones first. Let's say that I made a decision to accept the lot or accept the process, pass my sampling. And the correct decision indeed was to accept, right? That it was within conformity and acceptable limits. I made the correct decision, and we're going to call this the confidence, or my 1 minus alpha. And we'll see why it's 1 minus alpha when we talk about the errors. I'm going to go cross corner now, and let's talk about the other right decision that I made, the other correct decision that I made. If in my sampling, I draw the decision, I come up to the conclusion to reject the lot, reject the process, fail my sampling. And indeed, the quality was low enough to where I should have done that. Once again, I made the right decision. It's the correct decision we made. We should have rejected. We made the decision to reject when we should have rejected. That's the power of your sampling plan. It's 1 minus beta. Let's talk about when we get it wrong, right? When we get it incorrect, or when we create an error because of sampling, I make a decision to reject. Okay, so I make a decision to reject when I should have accepted. We call this the type 1 error. It's my alpha risk, right? And alpha is just the number that we use to assign a numerical value to the risk that I'm willing to take on. We call this the producer's risk, or the false alarm. And the reason why we call this the producer's risk, think about, and I always like using manufacturing analogy because a lot of people can relate to it. If I have a perfectly good component and I decide to reject that component. When it was a good component, I could have sold it, right? But I didn't. That risk is on me as the producer, right? It's lost money. It's basically taking something good, throwing it in the garbage when it could have went on. So ultimately, that's a business or a producer's risk. We're losing opportunity for profitability. Cross corner now. Cross corner is my type 2 error. This is when I've made an accept decision when I should have rejected. We call that the type 2 error, the beta risk, or the consumer's risk, or an escape. The reason why we call it escape or consumer's risk is because, again, using that manufacturing analogy, I have a bad unit. I have a non-conforming unit in my hand, and I make the decision to let it go. I allow that to go on. That risk now gets transferred to the consumer. Right? They are now receiving a non-conforming part, and depending upon the industry that you're in, that could be a very bad thing. So that risk goes on to consumer, and in effect, it's an escape. It should have been detected in my sampling, or it should have been detected in my inspection, but it missed. It escaped and went beyond that control. So those are the two risks that we're going to look to balance. And what we're going to find when we do statistical sampling, and I'm going to go out on a limb and say most of your procedures will talk about one of these risks and not the other, or at least emphasize one and not the other. When it comes to our incoming inspection, very often you have AQL tables that we're looking at. AQL is my acceptable quality risk, and that's going to be focused more so around the producer's risk. We're looking to minimize the producer's risk, which is odd to some extent, but basically we're creating sampling plans that will routinely pass. And we're going to see that when we go into the, we're going to go back into OC curves real quickly or shortly. But some of our procedures are geared more around minimizing alpha risk. Then there's other procedures that we have that are generally around reducing the beta risk, our validation procedures, or our CAPA verification of effectiveness sampling procedures. Those are going to be tied more so to minimizing my risk of compliance or minimizing my risk to the patient. And we're going to create sampling plans that are focusing on that. But not very often do we talk about the business and balancing the two. And that's what I want to go through here. Right? I want to be able to show that we could balance the two of them. We could meet the requirement of minimizing risk for the consumer, commensurate with or striking that balance with the risk to the producer as well. So when we're putting these sampling plans together, right, and the original version of this slide said passing a statistical sampling plan doesn't guarantee 0 failures, right? And usually I say that because very often we're talking about A = 0 sampling plans. And just because you have an A = 0 sampling plan, and management doesn't like to hear this, they assume, hey, we didn't see any failures and it's never going to fail. Not true, right? It's only going to not fail to the level that we validated to or that we've sampled to. So I've changed the wording on this slide since last time. You may have seen it if you've been through one of my presentations before. And passing the sampling plan doesn't guarantee an exact conformance rate. As I mentioned before, based on the sample that I have, the actual non-conformance rate of the population could vary, but I am going to make an inference or a decision based on the sample. However, it does provide a statement of statistical coverage, and this is where we're going to talk about that confidence and reliability, right? How the more information I have, the more confident I could make my statement, and meaning I've lowered the risk of making a wrong decision, right? That's basically what we're talking about here, of a certain performance level. Now, apply to process validation, but you could easily extend this process validation to CAPA effectiveness or even the acceptability of a lot. If you have a large lot and you're pulling a sample from that. Basically, the statistical statement we're going to say is I'm 95% confident that the process is at least 90% reliable. Okay. If we're talking about defectives or percent defective, what we're going to say is I'm 95% confident that the process defective rate is no worse than 10%, right? That whether it's a again product, right? That the actual nonconformity rate is no worse than 10%, is what we're able to say. If it's test method validation, my misclassification rate is no worse than 10%. If it's a CAPA verification of effectiveness, then it's the failure rate of that corrective action is no worse than 10%. It could be much better, right? And what we're going to see is it probably will be much better if we pass the sampling. But this is kind of like the guarantee or insurance policy that you could sign up for, right? You can't say anything, you can't guarantee anything better than the 10% at that confidence level. Now, we're going to start getting a little heavier into the math, right? I'm going to try to ease us through it. So we, I know it's kind of late and I don't want to get too technical, but these curves, before we go back into operating characteristic curves, these are curves that we can put together to demonstrate why these things work. Okay, this distribution here is a binomial distribution. Why binomial distribution? Because as I do my sampling, as I do my inspections, I have one of two options: accept or reject. Accept or reject. And what we do is we create a binomial distribution for the sampling plan. So again, we're bringing back that n equals 29, a equals 0, right? Except on 0 nonconformity sampling plan. And I want to demonstrate what that means, right? Using this binomial distribution. Let's say that my actual lot percent defective, that the population that I'm drawing from, in effect, is 10% nonconforming. So I know it's I know it's 10% nonconforming, and I'm going to take a random sample from it. I will pass that test, right? I'll basically say, let's accept this lot. Let's accept this lot exactly 5% of the time, right? And if we look, just interpreting the graph here, I'm accepting on 0. So if I look at my x-axis, that's the number I'm going to accept on. And since I agreed to accept on 0, I shaded only that bar in green. And what we could see is that that's about 5%, right? So 5% of the time, I will accept, I will pass that sampling. And I'll fail 95% of the time. This is where the confidence comes in, right? The confidence of this sampling plan. This happens to be a 95-90, right? Meaning 95% confidence, 90% reliability. This becomes the definition or the math behind why this works. Basically what we're saying, if I fail 95% of the time, what I'm saying is 95% of the time, I'm going to make the correct decision. 95% of the time, I'm going to make the correct decision. I'm going to reject that lot at exactly 10%. Okay. And I'm only going to pass it 5%. That's my beta risk. My beta risk is 5% of the time. This is 10% or greater. I may accept that lot. I threw an extra data point somewhere in between. Somewhere in between, I said 1%. Let's say that now I have a 1% defective lot or process running, and I sample from that. I pull the same samples, n equals 29 samples, and I agree to accept on exactly 0 nonconformities. I will see then from this binomial distribution that 0 will happen approximately 75% of the time. Meaning if the actual lot is 1%, and I pull this 95-90 sampling, if it's 1%, I have a 75% chance of winning or passing that sampling, which is much better than before. It's still not, I still have a 25% chance of rejecting, meaning that even 1%, which is much greater than 10%, I still have a fair chance of not passing that sampling. Whereas now I pull in the true AQL of this sampling, right? Which from a lookup table or through iterations, we could determine is 0.18% if my lot if my population has an actual lot percent defective of 0.18%, I will accept that lot 95% of the time. Okay. Much greater than 10%, right? But I'll accept that lot 95% of the time. And this is what I was saying before. The actual performance, if you want to stand a good chance of passing your test, your actual performance needs to be much greater than the reliability statement that you're trying to make in order to pass. And in this example, this A=0 sampling plan, we see that it's got to be significantly better. It's got to be less than 1%. It's 0.18, almost 0.2%. And then I'll pass that 95% at the time. And then I'll fail 5% of the time. Okay? This is our alpha risk. That's the producer's risk at that point, right? So the 5% here is going to be our alpha risk, where we reject something that it's way better than the 10%. I should have accepted it, but 5% of the time I may still reject even this lot. So that's some of the math kind of behind it that demonstrates the probability of passing any sampling plan that we put together, whether you pull it from a table or we follow the process I'm going to be teaching today. You could use these binomial distributions to demonstrate what your probability of passing for a particular sampling. So with that said, we're going to bring back the OC curve, and we're going to, and I got rid of the ideal because when we sample, the ideal is no longer there. And now what we're going to show is, what is the AQL and the RQL? I talked before about in the ideal case, the AQL and the RQL were equal. They were on that line, and to the left of that line, I'll always accept, and to the right of that line, I'll always reject. But here it's not quite that clean. There's a probability of accepting no matter where you are on this continuum. And what we see is the RQL and the AQL start to spread apart from one another, right? Meaning I'm highly certain on my AQL, I'm going to be highly certain about that acceptable quality level that I defined. 95% certain, right? 95% of the time I will accept when I wanted to accept. Conversely, on the RQL, we're going to see on the right-hand side, the red line. So the green line is my AQL level. The red line, the red vertical line, is going to be my RQL. And what we'll see here is I'm 95% confident in this sampling. I'm 95% confident that I will reject when I wanted to, right? So I've clearly defined those, highly certain, 95% in both cases. What happens in between is what we're going to call uncertainty, right? And to say uncertainty, it's not completely blind. We kind of know to what level of certainty, but it's not that high level of certainty that we're looking for. It's not necessarily at that 95% level confidence that we're looking for. It's something in between, and we want to be cognizant of that. We want to know that if there is if we do pass or fail this, right? If the actual lot percent defective falls somewhere in here, there's a bit of uncertainty of whether we're going to pass or fail, right? So we are looking for the very good or the very bad. So let's talk about how to create one of these. And again, if you have your organization has SOPs and work instructions where you have the lookup tables, you probably already know, again, many times they're risk-based. So you start off looking at the attribute that you're making an assessment for. We go to our risk documentation. We determine what level of risk is associated with the nonconformity of that attribute. We then, based on our SOP or work instruction, we determine what level of confidence reliability we need to make commensurate with that risk. And then we usually go to the end of our document where there's lots of lookup tables, and we pick one that we'd like. Management will always look for less samples, but I would caution against that, and we're going to see why. You want to pick the right plan for the performance of your product or process. So let's create one. Let's go through doing one of these together, where we want to create an attribute acceptance sampling plan. And again, this is where this may deviate a little bit from your procedure. You may prove me wrong, and I have seen some procedures, very few, that actually do talk about both in a single sampling, but more times than not, you're either looking for the AQL or the RQL. In this one, we're going to do both. So we want to create a sampling plan that will routinely accept 1%. That's going to be our AQL, right? We're going to say, you know what, I'm perfectly fine with 1%. So much so, I want to accept that 95% of the time. Similarly, 5% is too much. Okay, I don't want anything worse than 5%. So I want to routinely reject that 5%. But I'm willing to back off on my confidence a little bit, only 90% of the time. So 90% of the time, I want to make sure that if it's 5%, I want to reject that. And then, so we're going to walk through how to create these plans and how to identify these plans. And then we're going to compare this with some alternate plans that we could come up with. So we're going to use this. We're going to use this 1% AQL, 5% RQL to create a particular sampling plan. And then we're going to compare it to other sampling plans that we could have chosen instead, right? Again, using the example of process validation, if my procedure told me the 90-95, right? Meaning that I need to be 90% confident that my process is 95% reliable or no worse than 5% defective. Your lookup table may have a couple options. A equals 0, A equals 1, A equals 2, A equals 3. We're going to compare to some of those and see how forgiving or how stringent they could be when you know that there's actual defect rates that you should be considering so that you don't falsely reject. And again, we could do this live demo, but we will be providing the slides afterwards. So the slides will be available, and then the recording as well. We usually make the recording available as well. So you'll have an opportunity to step through this yourself in Minitab, or if you have other statistical software, you may be able to kind of draw the parallels. But we're going to step by step kind of go through. If you were in Minitab, there is an acceptance sampling function. So we would find that under stat quality tools, acceptance sampling by attributes. That is an attribute test, pass, fail, or accept, reject. And then this would be the configuration. We would select the fact that we want to create a sampling plan. We'll see in a few slides, we'll see the other option that we have. It's go, no go, meaning the defective rate. It's going to be specifically percent defective that we're looking at. And here is where that information that I gave you before, right? That 1% acceptable, right? That's my AQL. I want 1% AQL, 5% RQL. And down below is where I have my alpha and beta risk. So I have to do a little math, right? In our example, I talked about confidence levels. I said for my AQL, I want 95% confidence, or I want 95%, I want to pass that 95% of the time. And for my RQL, I wanted 90% confidence, or that I would properly reject that sampling 90% of the time. So we put those in the producer's alpha or consumer's beta risk respectively. We put those complementary numbers, the 5% and the 10%. And then we click OK to create the sampling plan. And you'll see in Minitab or whatever software you use, there'll be some tables and there'll be some data and things like that. But the visualization is usually, where you can draw a lot of this information. And I've projected similar lines here before, right? As we did before. The green lines represent my AQL. The red lines represent my RQL. And we could see here that curve that 1%, if the population is 1% defective, I will routinely accept this. And when I say routinely, 95% of the time, just like we wanted. Similarly, if my lot is 5% defective, I will reject that 90% of the time. Right? I have a 10% chance of accepting that. We see here up above that the actual sampling, it tells us that, one, the sample size is 132 units, so you need 132 units. And accept on 3, meaning in that 132, you can have up to three, and you could still accept. That fourth one will put you over the edge and you would have to fail that sample. But the third one you could still accept and say, and you could make the statement. Right? So if you pull those 132 samples and you do your inspection and you have 3 or less nonconformities in that sampling, you can then make the statement, I'm 90% confident that my process or that lot or what have you is at least 95% reliable. Or I'm 90% confident that the nonconformance rate, the nonconformity rate, is no worse than 5%, right? It's 5% or better. That's the statement. The last point that I want to make on this curve is the shape of that curve. Remember before that A equals 0 sampling plan looked like an exponential decay almost, right? It dropped off very rapidly. It started off near 0, right? And or near 100% when it was 0% effective, and it dropped off very rapidly. Here in this case, it starts off a little bit more gradual. Right? You got a little bit more of a curve here, a little bit more of an S curve, if you will. And what that is that's allowing us up to 1% effective. That the rate of that decay is much more gradual, such that it'll give us at least 95% chance of passing. Anything beyond that, and it starts dropping off rapidly, right? We start dropping off rapidly such that the probability of passing will decay very rapidly, and right up until we get to that 5% where we will routinely reject. So this is, and again, if you have these in your lookup tables, very often there may be AQL, RQL in there, depending upon the source of those tables. But if they're not, you now have a tool that you can use that can give you something otherwise if you know that. And where would you use this? Where would you use this? Very often if I'm doing like a human error thing, right? Let's say I have a CAPA and we know we have some human error and things of that nature. I could put all the controls that I want in place. I still can't guarantee 0 failures, right? There's still going to be some failure rate. But if I need to minimize my risk to the level of 95% reliability, but I'm willing to accept something a little bit less than that, right? And it's commensurate with the risk that I have, and it's within acceptable risk levels. This is when I would want to apply this, right? It's a little bit more forgiving. And even if you have up to 1% nonconformities, you can put this in place. Now, if you wanted to put additional controls in place, you could put secondary inspections and things of that nature. But realistically, right, if you're driving risk to lowest practicable, and you know that there's some conditions that you just can't surpass, but there's a rejectable level that you need to protect against, but there is an acceptable level that is within reason. This is when you would want to do that. And the reason why, we'll see, we're going to compare some plans, and then we're going to have plenty of time for Q&A and things of that nature. But we're going to just walk through, how do I compare a plan? And once again, we could do this in these charts, even if you have lookup tables, even if you have the lookup tables in your procedure. I've never seen one of these charts in a procedure. So these charts will help visualize, again, over that entire continuum, what's going on with your different sampling plans. So we're going to enter that the same way, right? So in Minitab, we have the acceptance sampling by attributes that we get to through the stat quality tools option. And now what we're going to do is it's that second option. Instead of create a sampling plan, we're going to compare sampling plans. So we're going to select the option to compare sampling plans. We're going to stick with the go, no go effective. We're going to stick with % effective because that's how we're designing these plans that we're talking about tonight. And we want to compare, and you can compare up to as many as you want, but we're going to compare 4 different sampling plans. We're going to put the one that we had in here. So the 132 at 3 is in here, but we're going to look at some other ones. And again, I have some lookup tables that have all these in here. The 306, that last one, I generated that one because none of my tables went up that high. but I just wanted to show what that looks like. So we have 45. So we have 4 different sample sizes. I'm sorry, 5 different sample sizes. I have n equals 45, n equals 77, 105, 132, and 306. And if you're in Minitab, the way you do that is you just enter the number and put a space. You put a space between each one. So Minitab will read this as 5 different sample sizes, and then Minitab will also be looking for 5 complementary respective acceptance numbers. And then we put those in 1 space, 0 space, 2 space, 3 space, and then in the last case, it's 10, 306 I can accept on 10. And then we click OK to view the sampling plans. And once again, you'll see charts and things of that nature. But what's always most interesting to me are these charts. And in this chart, again, I've projected several lines, and not to make it too busy, I didn't put the actual AQL levels, but I did draw lines where the different AQL points are for the different curves. And I figured out where those were, well, 1 for my table, but 2, that 95% line that runs along the top. We'll see that as that 95% line runs along the top and it intersects one of those curves, we drop a vertical. That's the AQL for that particular sampling plan. And we could see how much that varies. We could see that on the lowest end, it's something well below 1%. It's a fraction of a percent. I think it's close to 0.1, to be honest with you. So I think it's like 0.1% is that lowest one. Where that last one I created was, hey, let's say I want to, I find 2% acceptable, right? We could see where that lies on this curve, right? And we could see any one of those will give us a 95% chance of passing. But the interesting thing is where that line for the RQL gets intercepted. So again, if I'm going with that 90% confidence or 10% beta, and I draw that line across, I see something very interesting. Every single one of those samplings converge at the same point, right? And it's at 5%. This is where, from that risk-based perspective, that quote unquote statistical coverage, or I like to say the insurance policy, right, or your guarantee, right? Any one of these plans will allow you to say, I'm 95% confident that my process is at least 95% reliable, right? Or my defect rate is no worse than 5%. I could make that same statement for any one of these. But my probability of passing is going to be, knowing that my probability of passing is going to be dependent on my lot percent effective, I may choose, even though the cost is a little bit more, I may choose a higher sample size with previous knowledge of my process, expecting a certain quality level, right? So if I know that I know that I can't make 0.1%, right? I know that based on my knowledge, right? I mean, you may have a better process that can, but based on process knowledge, if you know that you can't pass an A equals 0 sampling plan, don't use an A equals 0 sampling plan just because it's lowest sample size, right? Use your process knowledge to select the right sampling plan that will guarantee you the confidence and reliability statement that you need to make, but also increases your probability of passing with a known nonconformance rate. So in this particular example, your AQL is going to vary depending upon which sample that you choose, but you'll always be able to make that 90, 95 with any one of these sampling plans. So that I was kind of driving you to this punchline, right? This is the part that very often folks lose that understanding when you just have the bespoke lookup tables where you just go to risk and you look at tables and you see a whole bunch of selections and you're like, I'll take I'll take the lowest sample size for $10, Alex, right? We're not doing that anymore, right? Now you have knowledge of your process. You could look at these tables, or you can go into statistical software and you could generate a statistical sampling plan that gives you the guarantee that you need, but also increases your probability of passing with an acceptable quality level that you're willing to take. And with that, there's one more parting gift, if you will, within the slides. If you don't have the tables, here's an example of a table that you have. These are all A equals 0 sampling plans. This will be common that you'll see in some procedures. And you'll see different reliability levels and different confidence levels. And more times than not, your risk documentation or your validation documentation or whatever SOP requires you to do sampling will tell you what confidence and reliability you need to make, whether it's a 90% or 95% confidence. Usually those are two of the most common. And then you choose your reliability. You choose what sample size n that you need for a equals 0. And if you don't have this table and you don't have Minitab, I gave you a couple handy dandy estimate equations down below. One is the general approximation, where you can approximate your sample size based on the confidence and reliability, and it's a ratio of natural logs. Or if you have a confidence reliability statement, you could take some known number and divide by your alpha figure. I'm sorry, your beta figure, to determine how many of these what's it called that you need. I'm sorry, not the beta. You're dividing by the lot percent defective, right? That level that you want to be able to reject that. You divide by that, and you could come up with some number similar to these as well. So giving you a couple tools. The big one is the software. Actually, the biggest is the understanding through the software. So that even if you have these procedures, you'll still have that deeper understanding. You'll have your procedures, and when you don't have either, here's a quick lookup table. And if you don't have the lookup table handy, here's a couple quick equations where you can estimate sample sizes. And by the way, when you're calculating sample sizes, always round up. So if you come up with some number that's a fraction, always round up to the next level integer. Any of these sampling plans, consider them minimum. These are the minimum number of samples. If you throw a couple more samples in there to round it out for some reason, you'll still be able to make the confidence and reliability statement that you need, so long as you meet the minimum sample. So what did we go over? We talked about what attribute acceptance is all about. Why do we do it? We even talked about a couple of examples, practical examples, and that was not exhaustive, but those are the most common ones that I usually get involved with. We talked about the ideal acceptance curve and the effects of sampling, and how that curve changes, as we're going to sampling, and the sampling error that we could make, and we kind of tied that to the OC curve and things of that nature. And again, we wrapped up with how to select your own sampling plan, not just with software, but now thinking about AQLs and RQLs. If your procedure has different options, you can now think about which one you want based on having that process knowledge. And with that said, again, always open to connect. If we're not already connected on LinkedIn, I encourage you, reach out. I always like talking anything stats and connecting with other professionals in the field.